Okay, here we are at the physics video lecture, psci 168, video lecture 24. This is the first hour after the exam, and I have not yet graded the exam as of now. However, I'm going to review the exam and review what we have left off with. So without further ado, we're going to talk about the exam, and we're going to then talk about thermodynamics. So in a sense, this is all review, but of course we've taken the exam now. And let me just say, very important, if you've made it this far in the semester, regardless of what the points are here, there should be no giving up, okay? When the time comes to add all points up and dispense grades, then various and assorted adjustments will be made. Because I know that with all of the notes that have been coming in, people have been working a reasonable amount, and this is an explosion of knowledge. So it's actually difficult to learn all this stuff at the speed that we're doing it, but we're all doing our best, okay? So without further ado, let's talk about what the questions were. The first question on the exam was to define force, work, energy, power, okay? So force, work, energy. Did I ask for conservation of energy as well? Power. And the idea was, starting with force, is a push or a pull, because we really just start with our muscles. Push or pull, it's a muscle sensation. The unit of force, to do the old square bracket here, is the Newton. You can write it out or just capital N, that's the unit of force. And a numerical example, I could think of a couple here. My weight, my own weight, approximately 850 newtons, let's just say. We could also say weight is equal to m times g, right? That's part of our repertoire. And then I could say, suppose it were 85, it's going to give you that number, 85 kilograms times 9.8 meters per second squared. I think that's 833. I just multiplied that out a little while ago. 833 newtons. So that would be an example of that type. Now you can do the same thing with work. So then the work is a force times a displacement. Its units are the Newton times the meter, which is the joule. And you know, an example is climbing the stairs. Okay. So you can do the stair climb example. For example, work, since we know we've got a force times G, we have mgh. In fact, this is our most important example of work and energy and all those things, okay? So I'll just write here, etc. Depending on how much time you have, you know, you can plug in more or fewer numbers. Energy is the capacity to do work. To do work. Okay. Capacity to do work. And so energy also has the units of joules. Not only that, but this example of work here could be thought of as potential energy. Depends on how how you're looking at things, what you're relating it to. So we have energy, we have potential energy, mgh is an example. We have kinetic energy, you have mv squared. I'm going to talk more about energy conservation later in the hour anyway, that energy can convert from one form to another. lots of stuff to say about that. And then finally, the power is energy or work per time. So its units are joules per second or watts. And then the power formula we had later on in problem 5 anyway, you know, M over T GH, for instance. Okay. Yeah, so that's what problem 1 is about. And of course, depending on how much time you have, there's just, you could explain all of these things and then run out of time. So obviously we're under time constraints. But when you review this, and you should review it often in the course of the semester, because the more you go through this whole thought process, the more you'll understand it, okay? None of these things work the first time through. Yeah. So that's the first problem. Then we had the question about the shape and size of Earth, because I want to see some actual calculation. So problem 2 is the shape and size of Earth. And the argument about the shape, you could say, there are a number of arguments to figure out what the shape is. Phases of the moon is a good one. Phases of the moon. So you come to the phases of the moon, and then eclipses tell us about the shape, which is the sphere. Okay. Now for the size of the Earth, we have Eratosthenes. Right? You can look him up and find his exact dates, a couple hundred years BC. But he has this construction, and so what we wanted was this construction here labeled and as much as possible understood. We have parallel rays of the sun coming in. This point here, one of these is Aswan and one is Alexandria. I'm just gonna, this is Aswan here, I'm gonna use B for Alexandria. So you can measure the angle that the sun makes at noon with the vertical. And if you assume these sun rays are parallel, then your construction tells you that that angle you measured is that same angle here in the Earth. Here's the radius. And if you know this arc distance S, you have a well-defined geometrical problem. And you can say that my angle theta is to 360 degrees. It's the same ratio as S is to the circumference 2 pi radius. So once you have this idea, the rest is just algebra. You can solve for R, and then you find 6.38 times 10 to the 6 meters. Okay. So yeah, that's the shape and size of Earth discussion. A lot of things, and on these exams and the one to follow, if you're better at just discussing the background, then you stress that, and if you're better at doing the calculation, you stress that, okay? Main thing is that you present what you've learned. But yeah, this was one where we could do this construct here and explain it. Okay, so that's problem 2. Problem 3 builds on this. We were talking about the speed of a satellite in near-Earth orbit. And that was an important problem for a number of reasons. It made use of the law of free fall. It delivered an important speed. That 7,900 meters per second gives us an idea of the magnitudes of what we could say are astronomical speeds. Okay? So actually very important. So here we are on problem 3, which is satellite orbits. So first of all, you need to know the conditions, and basically the condition is frictionless motion. So no friction. And what you have under those circumstances, if you're close to Earth, you just have free fall. And free fall, if we drop something, it falls a distance h half gt squared. So if you drop it from rest, after 1 second, 2 seconds, 3 seconds, it falls that distance. And we also have the horizontal throw. So if we throw something horizontally, it just takes a curved trajectory. So we put those things together, got that, that's right. We put those together and we imagined launching something close to the surface of Earth horizontally. Here's where my red pen comes in. It actually falls around the Earth. Just keeps going around the Earth. So here's this construction. There's the center of Earth, that's a radius. There's a hypotenuse, so we have the radius here from the center to that point. We're moving forward a distance L and we're falling a distance h. And h is just stated right above here. So the way we find L, which was the distance that we fly forward in 1 second, okay? Distance forward in 1 second. So we find L by using the Pythagorean theorem for this right triangle. R plus h, the quantity squared. You expand this out and you say h is small, or h is much less than capital R, and you get this approximation that is a very, very good approximation. 2 times R times H. After 2 or 3 lines of algebra that we've done a couple of times already, and they'll find those in your notes. Okay, so fine. And then V is equal to L divided by T. Okay. Distance over time, that's the speed of the orbit. And L is the distance we move forward in 1 second, and T is then 1 second, okay? But yeah, I threw a little twist into it because I gave you some data for Mars. So the orbital speed for Mars, do I have room here? Sure, let's squeeze it right in here. So for Mars, we have L equal to the root of 2 times the radius of Mars, and that was 1.74 times 10 to the 6. 0.74 times 10 to the 6 meters. Okay. And then the H was 1/2 1.62 times 1 second squared. Okay, so this is meters per second squared. So that's 0.81. And of course that 2 times 0.81 gives us back the 1.62. But yeah, if you multiply these together, you get 1,679 meters. And so I'll write V orbit for the moon. Did I say Mars or the moon? It's the moon. Okay. V orbit for the moon is equal to 1,679 meters per second. Okay, so we're rocket scientists at this point. And what was it for Earth? For Earth it was 7,900. So that gives you the magnitude of these speeds of things. And these two problems, you know, they seem to have gone away from the energy problem, right? Because they're more geometry and astronomy, but we had to know these kind of speeds because we know that a moving object has kinetic energy, and kinetic energy is one of, we can't understand energy without knowing about kinetic energy. And we even took a detour in this during the semester. We talked about the kinetic energy of an asteroid that comes in towards Earth, collides with the Earth, and for that we had to know have these types of ideas here. And the G comes up in the expression for the weight, and it comes up later on in the expression for the potential energy. So, and originally it comes from free fall. Okay, so yeah, that's why I insist on us going through this whole development there, so you really understand what's going on. So 1, 2, 3. So problem 4 and 5 were both hydropower related. So for problem 4, hydropower is what this was about. So the water stored behind a dam is potential energy. I'll go ahead and draw our little picture. Picture's always good. Water stored behind a dam, it's potential energy because it is, that's the powerhouse there. Potential energy because it's above the powerhouse. So there's a height h involved, and it is potential energy. Potential energy, so mgh. If this lake were somehow, for example, here in the Central Valley, no potential energy, it's down at the bottom of the valley. It has to be elevated, so we have the elevated water mass, and that represents as much potential energy, as much work as it would take to lift that water from down below up above. Generally, the sun does it for us, and we've got our water cycle. Okay. But with pumped storage, we actually ship energy over here and pump it up the hill to store it as well. Okay, so this is really central to the entire course, this basic potential energy expression for lifting something. Work you do, you can get it back again. Okay. And then the rest of the problem, we had to fill in a bunch of numbers. So the mass can be written as density times volume, and then we have G and H. And yeah, those numbers, let's see, what were they here? So for the density, we have 10 to the third kilograms per cubic meter. And then for the volume, we had 1,000 times 500 times 40. So 1,000 times 500 times 40, and that would be meters times meters times meters. So meters cubed, and we would cancel those. So now we've got kilograms. G is 9.8 meters per second squared. H was what, 600 meters. So, can we fit this all in the bottom here? I think we can. So when we multiply that out, we get 1.176 times 10 to the 14. 1.176 10 to the 14 joules. All these things, consistent units, multiply them out, you have joules, energy units. Now what you can do is take that answer and then say 1 kilowatt hour is equal to 3.6 times 10 to the 6 joules. So that's how you make the conversion. I'm dividing this number by 3.6 times 10 to the 6 joules. And in that case, the joules cancel, and I'm left with some number of kilowatt hours. I have here 3.27 times 10 to the 7. Let's write that one clearly. 3.27 times 10 to the 7 kilowatt hours. Okay, it's squeezed in there, but you see how that goes. 3.327 times 10 to the 7. So let's ponder this again. I'll put a little blue water in our reservoir. Okay, we've got the blue water, it's elevated above this lower lake level. And simply by knowing the volume of that lake, which you can actually get if you know how to read a topographic map. Read a topographic map, you figure out the volume of a valley, say. Engineers say, good, we'll put a dam in front of it, and now they know how much, and if they know how low the powerhouse is going to be, they immediately know the potential energy of that water. And by the way, the lake could drain more than once per season because there's snowmelt coming in all summer, okay? So it's not a one-time deal, but nonetheless, you know that potential energy in joules, you convert it to kilowatt hours. Now that's just a big number, but you could add up all of your electricity bills, the kilowatt hours on them, and figure out how many you have per year, or for whatever time you want. Say per year, and then you could say this amount could serve so and so many households per year, okay? And that's how it's done. Okay. In reality, you'd have to take this number and cut it down a fair amount because of friction and inefficiencies and electrical transmission, but this is the base amount that you're starting with, and you certainly can't get more than that. Okay, so like I said many times, this is a central part of the whole semester where we can judge the amount of energy needed, you know, to run civilization. Okay, so to wrap that up, I had a fifth problem using the power formula. So problem 5, what were those numbers there? It was the power of water flowing over Niagara Falls. So the idea was flow rate times G times H, and what did we have for the number? It was some pretty impressive number. It was 1.2 times 10 to the 6, 1.2 times 10 to the 6 kilograms per second. That's the flow rate, the M over T. We've got 9.8 meters per second squared, and we have 50 meters. And that gives us 5.88 times 10 to the 8 joules per second. These are consistent units, and so that's watts. Okay. And yeah, that's a large number, 588 million watts, just over a half of a gigawatt, half of 1,000 megawatts. This is the kind of power that a modern power plant delivers. Be it a hydropower plant or a coal-fired power plant, gas, you name it, nuclear. These are the orders of magnitude, and even larger numbers than this are delivered by a single power plant. Okay, let's check the time. Okay, good, we've got nothing but time. Okay, so that's the review, and the repetition is good. So, you know, you want to go over this, have good, clear notes. The best notes I'm seeing is if you space them wide enough, room for comments, room for additions, room for your nice little pictures, and so forth. Okay. Now, you'll notice we didn't even get into thermal physics on this exam. We've covered so much material. Thermal physics will come later. But I'm going to spend the next few minutes repeating some material and giving a little different presentation of thermodynamics now. So up until here in this set of problems, we have work and energy, and we realize that energy is converted from potential energy to kinetic energy and back and forth and that kind of thing. So that's where I'm going to pick up. When I talk about thermodynamics, I'll go ahead and leave those topics up there. The first law and the second law. So this is where I can spend a little more time talking about conservation of energy. So laws of thermodynamics. Laws of the first one is conservation of energy. And then we say in words, energy can be neither created nor destroyed. We know about energy changing form. Okay. So energy is not created, it's not destroyed. In that sense, it's not lost, and it doesn't come from anywhere. So energy cannot be created, cannot be destroyed, but it's something that changes form. And of course, we know what energy is: capacity to do work. Okay. So conservation of energy and that law, we can kind of illustrate by, we have work, we convert that to kinetic energy, it can go back to kinetic energy plus work, it can change form. So energy changes form. But until we talked thermal physics, we simply did not have a complete idea of it, because it can also be turned into heat, right? Thermal energy. And then it seems to be lost, because I could do some work. Here's a good example of work. I do some work on this box here. I give it a push, slides across the table. Give it a little more room here to slide. It slides across the table. I did all that work, it came to rest, so I gave it kinetic energy. It no longer has kinetic energy. But it rubbed the table surface, and even though we can't feel it with our hands, we know that heat was created. Heat was created on the table, was created on the bottom of the box, and then that heat dissipates and it seems to be gone. But it just spreads out. Okay. So what we're talking about here, energy changes form. I can barely read my own writing sometimes. So the general law of conservation of energy is the first law of thermodynamics. Here, I'll give them Roman numerals. First law. Okay. Second law is that entropy of a closed system increases or stays the same. Now, this was a more technical. Okay, I'm just going to write increases. The entropy of a closed system increases, and then we say delta S total is greater than or equal to 0. Okay, so the change of entropy is always positive. Now, this one is technical, but we're going to need it to understand converting heat into work, the heat engine. So it's worth reviewing this once again. So we have, for the change of entropy expression, I'm going to write it this way. If heat flows into something at temperature T, I'll label them this way. This is 1. If heat flows in, then we have delta S is equal to Q divided by T. We can put the absolute value sign to make sure we know that's positive, and T is in Kelvin. And the second one, so this one is heat flows in. Let's go ahead and label that. Energy flows in to something. So there's the change of entropy of that object. Then, go ahead and erase this. So yeah, the second one is that if energy flows out of something, so point 2 under this development here, energy flows out, and then delta S is equal to minus Q over T. So those are basically the rules. The units here, again, T are in temperature in Kelvin, so the units of this delta S are joules per Kelvin. Yeah, so those are the rules, and what they reflect is the order and disorder. So if I bring energy into this object, it's being heated up, the molecules are moving faster, they're disordered. It could even be melting some water, okay? And then the ice, or I'm sorry, it could be melting ice, then the orderly ice turns into the disordered puddle of water, okay? So there's the change of entropy is the increasing disorder. Now if I have energy flow out of an object, for example, flow out of a bucket of water such that the bucket of water turns into ice, then the order is increasing and the change of entropy is negative. So order, disorder actually, disorder is increasing up here. Disorder increases. And on this one here, disorder decreases. Okay, that's kind of a double negative, but we can follow that. Not trying to be confusing. Disorder decreases. We're going to go orderly. And again, you could say something is melting or something is freezing. Good. Now after you have these rules, we have this example, which I'm going to explain one more time. So now with relation to this closed system, we just imagine putting an object at a higher temperature in contact with an object at lower temperature, so T hot and T cold. Okay. And we know that the energy flows from the hot to the cold. And if we want it to be a closed system, we put it in a cooler, okay? And now we calculate the change in entropy total for this cooler. We put the hot and the cold in, close the lid, okay? And the change of entropy total is the heat leaving here, so we have minus Q over TH, and that same heat is entering plus Q over TC, okay? So it's leaving the one and entering the other and nothing else is happening. So we can pull out the absolute value of Q and just do the cross multiplication. And we'll have, when we change the order, the TH is the one with the minus sign on it, okay? We cross multiply, we'll have TC times TH in the denominator and TH minus TC, right, when we cross multiply, TH minus TC in the numerator. And these are all Kelvin, so the denominator is just some number, and the numerator is hot minus cold, high minus low temperature, always positive. So here's the thing. I didn't have to invoke this law here. The rules told me that when energy flows from hot to cold, that the total entropy increases. Okay? So you can take this as one example of this general law, and the law is really that energy flows from hot to cold, or energy flows from the disordered to the ordered. Okay, so that's what the law is saying. It's very fundamental. The only way you could reverse this arrow in an isolated box like that is if the world were running backwards. So if you play a movie backwards, you can see things that are impossible, right? If you take a movie of an ice cube melting and you play it backwards, you have a movie of a puddle of water turning into an ice cube. But that's not real. And so this direction here is sometimes referred to, or the direction here, which corresponds to this here, is sometimes referred to as the arrow of time. So yeah, I'm just impressing on you that, yeah, I've repeated this example now, but I'm impressing on you that this is fundamental, and it's intuitive in the sense that no one would expect it to be the other direction. So it's a formalization of something that we always see, something that we never see the opposite case. Okay, I'm going to check the time once more. Okay, good. So we're not going to spend much more time today. We've actually done a really good review. When we got to here with energy and heat, okay, and entropy, we actually reached a pretty major stage. Now, I'm going to continue next time with heat transfer, and I have some demonstrations of that. You know, we can start reviewing the details of some of the heat here, but where we're headed is to understand heat engines. That'll take a couple more hours. Good. So yeah, just keep your notes good. If you ever find good pictures to illustrate these ideas, print them out and add them to your notebook. Other than that, we'll see you next time.